have the pleasure to introduce the next speaker, Mary Jane He from Oklahoma. She's going to continue the course about thermodynamical formalism.
Thanks very much for the introduction. Thanks to the organizers for the invitation. It's a great pleasure and honor to be here. So it's my first time in Trieste, but it's my fourth time attending BEYOND conference. So the first time I attended the BEYOND conference was in 2017 in Provo, Utah, when I was a graduate student. And I have been participating in BEYOND conferences ever since. So for the last three conferences in Marseille, Poland, and Trieste. So I've been learning a lot, and I hope the series will continue. So let's get started. So today I'm gonna continue our mini course on thermodynamic formalism in holomorphic dynamics. But I would like to start with Sullivan's dictionary. Okay, so there are two fields in mathematics. So one field is called Kleinian groups. And another field is called holomorphic dynamics or rational maps. So I will start with definitions. So what is a Kleinian group? So a Kleinian group is a discrete subgroup of PSO2C. And a rational map, a rational map is basically a holomorphic map F from the Riemann sphere, CP1, to the Riemann sphere itself. So it is a ratio of two complex polynomials. And what are some of examples of Kleinian groups? Well, we have seen lots of examples in Wenyu and Jialan's talks. So for example, the first example, you take a hyperbolic three-manifold, and you take the fundamental group of this closed hyperbolic three-manifold. It is an example of Kleinian group. So the fundamental group of the hyperbolic three-manifold will act on the universal cover of the hyperbolic three-manifold, which is the hyperbolic three-space. And this action will extend to the boundary of the universal cover of the hyperbolic manifold, which is the Riemann sphere. So basically, like, if we have a Kleinian group, it will act on this sphere at infinity of the hyperbolic three space. This is also because this group is the orientation preserving isometry of the hyperbolic three space that Wenyu told us in her first lecture. And another example, you take the representation of a surface group, a closed surface of genus greater than or equal to 2. You take a discrete faithful representation into PSO2R, right? So discrete faithful. And this is called a Fuchsian group. So it's the fundamental group of hyperbolic surface, right? It acts on the universal cover of the surface, which is the hyperbolic point. And you can also take a convex co-compact representation from this surface group into PSO2C. Right? So this is also an example of a Kleinian group. So here, there are lots of examples. Like you can cook up your favorite rational map, like take two polynomials, take their ratio, or you can just take a polynomial. Okay, so what is the story about these two sides of mathematics? Well, this begins with Sullivan's theorem. So I should start from this side. So So there's a theorem of Dennis Sullivan, which is called no wandering domain theorem. So what is this theorem? Well, this theorem says that if you have a rational map, and as Fabrizio defined, so we have a Julia set, and we also have a Fatou set, right? So basically, like you can think of Julia set as the support of the measure of maximum entropy, and the Fatou set is the complement. And you take a connected component in the Fatou set, and you look at its orbit, right? So, and a natural question in dynamics is this domain wandering? So that is to say, like, I take a connected component and I look at its orbit. Is it wandering around on this Riemann sphere? The answer is no. Well, this is proved by Dennis. So basically, like, if you look at the orbit of this component, it will eventually become periodic. And when Sullivan proved this theorem, he discovered that the proof of this theorem is basically a counterpart in complex dynamics of Alfor's finiteness theorem. So Alfor's finiteness theorem says if you have a Kleinian group, right, and we know there's a limit set defined by Wenyu before, and you look at the complement of the limit set, which is called the domain of discontinuity, and you ask if you have a finite generated Kleinian group, and this Kleinian group acts on the boundary sphere, which is the Riemann sphere of this hyperbolic 3 space, you ask what is the quotient. So Alfor's proved using complex analysis that the quotient is a finite union of Riemann surfaces, each of which is a compact Riemann surface with finite many points removed. Right? So this is the beginning of Sullivan's dictionary, because Sullivan discovered Alfor's proof. If you apply the ideas and techniques in complex dynamics, you will get this no wandering domain theorem. And ever since then, there were a lot of theorems telling us what is the analogy between these two dynamical systems on the Riemann sphere. Yeah. So if you have a finite generated Kleinian group, and it acts on the Riemann sphere, and you want to understand what is the quotient. So the theorem says the quotient is a finite union of compact Riemann surfaces, each of which is the compact Riemann surface with finite many points removed. Yes? Yeah, exactly. All right. And ever since, there are many people working on this kind of dictionaries. Maybe let me write down some names. McMullen, maybe Muir, Sullivan, Law, who else? Muir, maybe Bank, Mayer, and Pilgrim, Hysinski, and Lyubich, and including myself, and many others. And but I would like to point out that although all these people are studying Sullivan's dictionary is not an exactly dictionary. So this is to say that, so we have seen many theorems telling us what is the analogy between these two fields, but there's also non-theorems. So counterexample, non-example. So let me state from this side, this is a theorem due to Avila Lyubich, also Booth Chireta, that there exists even a quadratic polynomial, f, whose Julia set has positive Lebesgue measure. Right? So basically, like you take a polynomial, you look at the support of the measure of maximum entropy, which is a subset of the complex plane, and their theorem says there exists an example so that this set has positive Lebesgue measure. But this is not the case for Kleinian groups. So yes, so this is Alfor's measure conjecture. And by the work of Dick Canary, it is equivalent to the tameness conjecture. So basically, now it's a theorem. Let me just write the authors. So this is due to Ian Agel, Danny Calgary, Dave Gabay. So what does this say? So the theorem says, take a finite generated Kleinian group and look at its limit set. Then either the limit set is either the entire Riemann sphere or it has measure 0. So this kind of things in complex dynamics does not exist for Kleinian groups, right? So so it is interesting to discover what things are the same and what things are different. Okay, so now, given it's now 2025, over the last 20 years, so people have gone from Kleinian groups up, well, I wrote down, but to Anaso groups. So what is an Anaso group? So basically, you take the Anaso representation, right? So the image is an Anaso group or Anaso representations. All right. So these are, as we learned in another mini course, these are generalizations to Lie groups of higher rank of these convex co-compact representations from the surface group, or later Gromov hyperbolic groups, into PSO2C. So they want to generalize from PSO2C to Lie groups of higher ranks. And on the other hand, we have this rational dynamics on the Riemann sphere. So that's what we're going to do today. So we want to understand the quote-unquote rational maps. So that I will define in 2 minutes. Rational maps on higher dimensional complex manifold. In particular, on this projectivization of C, k plus 1. Okay, so and also I will just write CPK. Not like Wenyu, who keeps writing P of R3. Okay, so so now you can ask the same question, right? What is the analogy here and here? So, but what is the point? The point is both these higher dimensional or higher rank things are more complicated, as we saw in the other lecture. So they're less well understood, and it's more complicated to build an analogy. But from last Beyond conference in Poland to this Beyond conference, at least we're trying to fill in one entry here, which is the dimension theory. Okay, and so on this side, there's work of Yuxiang, Jialun, Wenyu, and Dishan, and also Francois, Pablo, and Rappaport. Right, so we have seen from the mini course 2 years ago, François and Pablo telling us the dimension, what is the dimension theory, basically the Legendre-Perriand formula for those unobservable representations, and also in this beyond, Wenyu and Jialun told us the dimension theory for these representations. So starting today and tomorrow, I'm going to tell you the dimension theory on this side. Okay, so that's kind of like a general introduction. Okay, so I'm going to start by telling you what are the maps. So what are the generalizations of rational maps on CPK? Okay, so these maps are called holomorphic endomorphisms of CPK. Okay, so I guess for this audience, you can think of its endomorphism map, like on this manifold, except you add one more condition that they're holomorphic. Okay, so, but I will start with the definition. So you take a map, we consider the map from CK plus 1 to CK plus 1, and this map should satisfy the following condition. So let F be such that 1, the inverse image of 0 is just the point 0. And if we write F in coordinates, so each coordinate is a homogeneous polynomial of degree D. So greater than √2, 2. So I want homogeneous because I want to projectivize. So this map will descend. So then this map descends to a map, small f, on the projectivization of CK plus 1, which is CPK, to itself. And this map is the holomorphic endomorphism that we are going to consider. And this is the holomorphic endomorphism. And this degree D is called the algebraic degree of F. So D is called the algebraic degree of F. Okay, so that's the map. And what do we know about these maps? So I should say holomorphic dynamics in higher dimensions started in the 90s, so which is 10 years older than the Maxwell representations. So we know, first lemma, the entropy of these maps, topological entropy. So this is Gromov-Yondim. So topological entropy of a holomorphic endomorphism of CPK of degree D is k log D. So k is the dimension, and D is the algebraic degree. Okay, and also there exists. This is true for all k greater than or equal to 1. Okay, and also there exists a unique measure of maximum entropy. So this is the theorem. Let me just write. Start with Lyubich in dimension 1. And Freire, Lopez, Magnier, and Brent Duval in higher dimensions, that there exists a unique measure of maximum entropy, and the entropy is k log D. There exists a unique MME for these holomorphic endomorphisms. Okay, so yes, so definition, then we just take the support of this MME as the Joule set. So the Joule set J of F is defined as the support of this measure of maximum entropy. Maybe I denote by mu. Okay, so yes, so now, just like for any dynamical systems, so if we have a holomorphic endomorphism, you take an invariant measure. So let's let nu be an maybe ergodic F invariant probability measure. So for any such measures, like from the perspective of smooth ergodic theory or ergodic theory in general, there are three fundamental quantities associated to the measure. Right? So the first is the measure theoretic entropy. So which I will denote by H nu of F. So I'm not going to define what is the measure theoretic entropy, or you just apply Brin-Katok. Okay, so I want to define Lyapunov exponent, because we will use some of the notations tomorrow. Of nu. So this is basically the oscillatus theorem. Okay, so what does this theorem say? There exist some numbers, L numbers, chi L, smaller than or equal to chi L minus 1 to all the way up to chi 1, with L in between 1 and k. So those are basically the Lyapunov exponents, such that for nu, almost every x in k, there's a splitting of the tangent space. There's a stratification of complex linear subspaces of the tangent space, where I denote the last one, which is the 0 inside L sub L at x all the way to L1 in x, which is the L1 of x is the tangent space at x. Okay, so such that we have, so basically it maps this Ljx to Ljx at f of x, and also you have the normal thing that you see in ergodic theory. So you take a limit as 1 over n of log of the length of the tangent vectors, and then it goes to chi of j for all vectors in the difference of these linear subspaces. So Lj, L plus 1, sorry, x, subtract Lj plus 1 of x. So for all j in between 1 and L. Okay, so this is the statement of oscillatus theorem. Okay, so, and also there's the third quantity, the Hausser dimension, that when you defined already, so basically, what is the Hausser dimension of the measure? So it's the inf, maybe let me just write. So it's the inf of a full measure Borel set. So Hausser dimension of x, where nu of x equals 1, and x is Borel, subset of CPK. Okay, so when k equals 1, as we already seen in Fabrizio's talk, there's a theorem due to Manier in general and Manning in the case of polynomials, which tells us what is the relationship with these three quantities if k equals 1. So this is a big assumption. Okay, so if k equals 1, we know this is basically entropy over Lyapunov, right? So dimension, House dimension of nu is entropy over, because you only have one Lyapunov exponent, I will denote it by this Lyapunov exponent, chi sub v, okay? Oh, chi sub nu, sorry. Okay, so I should just write a remark without writing all the details that in smooth ergodic theory, the relationship between entropy, Lyapunov exponent, and the dimension is also very important, starting from the work of, so in dimension 1, so smooth dynamics. In dimension 1, which basically means interval maps, so there's work of Hofbauer, Orith, and Ledrapierre. And in higher dimensions, well, the work really started from Passing. And Young. So basically like similar as in the other mini course, we will rely on some of the Young's result. And the Ledrapierre-Young times 2. And Barrera-Schmeling, Barrera-Passing-Schmeling. So for this audience, I'm not going to say what these theorems are, but just to give you some context where this result stands. Okay, so now, as I said, we want to move to higher dimensions. So we want to consider the very interesting case we want to consider is what happens when k is greater than or equal to 2 for CPK. Okay. So maybe let me start erasing here. So let me first tell you the bad news. The bad news is this theorem does not work, okay? And it's very easy to see why it doesn't work. Okay, so I can give you an example. So what is the example? You consider a polynomial from C2 to C2. So this is just like a multivariable calculus. So now you have two variables, Z and W, right? And it gets sent to somewhere in C2 by F. So now you take the first coordinate, you still keep Z, like Z squared. And the second second coordinate W, you take W squared plus maybe a little bit, like epsilon times I or something, right? So basically, it's a product map, right? And this is a polynomial map of C2, polynomial endomorphism of C2. And this map, in particular, extends to CP2. So C2 is not CP2, right? So at infinity, you have CP1. So this map extends at the CP1 at infinity to a holomorphic endomorphism of CP2. Oh, but this one is, the extended version is the holomorphic endomorphism. So yes. So basically, F extends to CP2, right? And complex number. Sorry, like okay. So U plus maybe I don't know, like 0.5 I. Square root of -1. Yeah. You just perturb a little bit. Yes. Yeah, extend. Yes, exactly. And then, okay, so what is the measure? You want to take, so for each component, you take the MME, right? So each component is a polynomial. You take nu I to be the MME of ith coordinate, where I is 1 and 2. And then you take their product. So, oh, what's that? Oh, yes, this is a different I from this I. And then let's calculate what is the Hausser dimension of this measure, right? So this measure lives on the higher dimension, CP2. Okay, so let's calculate what is the Hausser dimension of nu, right? So it's a product, so it's a sum of Hausser dimensions. Okay, but for each coordinate, right, I can apply this dimension 1 theorem. So this is entropy, which is, because it's MME, so it's log of degree, which is 2, right, by this theorem. Okay, so nu 1, okay, so log 2 of chi nu 2, right? So this is the dimension if I calculate. And then I want to, on the other hand, I want to calculate what is entropy over Lyapunov. So what is this one over, so in higher dimension it becomes sum of the Lyapunov exponents, right? So this is entropy, 2 log 2, right, k log d. The Lyapunov exponent is the sum. So you can see, like, you can find lots of examples where you don't add up like this, right? So the left-hand side, which is the dimension, is not equal to entropy over Lyapunov. So then the question is, okay, so this is wrong, but why this is wrong, right? And also, like, what is the correct answer? Why this is wrong? Because if you look at the formula, right, this is Hausser dimension on the left-hand side, and the right-hand side is entropy over Lyapunov. So entropy and both entropy and Lyapunov exponents are dynamical quantities. They see the dynamics of the rational map. But what is Hausser dimension? So Hausser dimension means you cover a set by balls, right? So in dimension 1, this theorem tells us the balls can see the dynamics. Why is this? So basically, like, this says in higher dimensions, this is no longer true, right? Well, because in higher dimensions, you have more dimensions. So the dynamics is not conformal. So in dimension 1, because you only have one dimension, the dynamics is conformal, which means you take a ball and you iterate is roughly a ball. So basically, balls can see the dynamics, right? And in higher dimension, you have non-conformality. You take a ball and you take an inverse image, it becomes an ellipse, and you iterate again, it becomes some random thing, right? So basically, like, balls are no longer going to see the dynamics. So if you want to understand what is entropy over Lyapunov, this dynamical quantity, you cannot use balls, right? So basically, like, this is why it fails. Okay, so then, what is the correct answer? Maybe let me erase here. Well, you have already seen the statement of the theorem. So let F be a holomorphic endomorphism of CPK. Yeah, k is greater than or equal to 1. So because we're going to recover Méniès formula. Okay, so holomorphic endomorphism of algebraic degree greater than or equal to 2. Okay, and then you take a measure, but we have some constraints on the measure. So let's nu be an ergodic, invariant, F-invariant ergodic probability measure with positive Lyapunov exponents, which means every Lyapunov exponent of nu is positive. Okay, and then for these measures, we have a theorem. Okay, so I will write down the statement. So this is volume dimension. So this, so basically we define a new dimension, which we call volume dimension. It depends on the dynamics of F and also the measure. So this one is going to be entropy over sum of Lyapunov exponents. So L nu, this is sum, oops, of Lyapunov exponents of nu. Okay, so this is our theorem. So for the rest of today, so for tomorrow, I'm gonna tell you like how to define this volume dimension and also how to prove this theorem. But I have 20 minutes-ish. Okay. Yes, so for the remaining 20 minutes, okay, 24 minutes, good. I will tell you what is the application of the theorem, right? So if you cook up a new dimension, what does it do for you? Okay. Yes. Yes, 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 because you're gonna see the dynamics. Yes. Yes, so basically, like House dimension does not depend on F, but it's because in dimension 1, there's like a distortion theorem, Kobe distortion theorems, which says like the inverse image of a ball, like which is dynamics, but it's roughly a ball. So like you can get rid of F. Okay, oh, I should say, sorry, I forgot an important remark, right? Why this is Magnier's formula when k equals 1. So remark. So if nu, okay, if all the Lyapunov exponents of nu are equal, so they're positive and equal. So basically, this means you're back to the conformal situation, right? So then we have the following. So twice the volume dimension of the measure is equal to the House dimension of the measure. So basically, like when you are roughly conformal, you can get rid of F. Okay. And in particular, in dimension 1, we get the Magnien formula, Magnien formula. Okay, so this is, I will leave here the statement. And I will continue here for consequences. Oh, sorry. I think there is also a 2. Yes, because this is, when we define this is real versus complex. Yes, sorry. Yes, yes, yes. And then why is volume? Well, actually, like, it's funny. So Fabrizio and I were discussing, and we were discussing something that reminded me of something that I learned from Amy's class when I was a graduate student, and that's basically volume. And we tried volume, and after 20 pages, it worked. So that's why it's called volume dimension. So if I have time, I will just say like where we use volume in the definition. But let me first finish the consequences. Okay, so the first consequence, so what is the consequences? So basically in dynamics, in particular holomorphic dynamics, there are other dimensions. So let me start. So these are basically results due to Denker-Urbanski. McMullen, and Przybylski-Urbanski. Okay, so basically, like all the consequences are generalization of these results to higher dimensions, except we need to replace the dimension with the correct one. Okay, so yes, so theorem 1. Consequence number 1. So we have, so for any F holomorphic endomorphism of degree greater than or equal to 2, we have the following. So I will write down 2. This is called dynamical dimension of F is equal to, so I haven't defined what are these numbers. Okay, so, so this P denotes, well, it's related to pressure, so it's basically the zero of the pressure, and this is the dynamical dimension. So maybe I write down the definition here. So dynamical dimension, so we only consider, in the applications, we only consider measures on the Julia set. Okay, plus means all the Lyapunov exponents are positive. Okay, so this is the soup of nu. Okay, so or maybe soup of volume dimension of nu, where nu is in this set of F invariant ergodic probabilities supported on J with all the Lyapunov exponents positive. Okay, so basically you take all these measures, take their volume dimension, and take the soup. So that's called dynamical dimension of the map. And then we define a pressure function. So maybe I define here. So P of T, also it's on the Julia set and the positive Lyapunov exponents. So this is defined as the variational principle. So entropy subtract T times the sum of the Lyapunov exponents. So basically this sum of the Lyapunov exponents is the integral of log Jacobian, right? So, sorry, integral of Jacobian. Okay, so, and then again, these measures are in the invariant ergodic probability measure supported on the Julia set with positive Lyapunov exponents. Okay, so, and then this small p, j, plus of f is defined as the inf of t, where this guy is less than or equal to 0, right? So basically, like you can prove, or we prove this pressure function is still non-increasing and convex. So like a priori, this number could be infinite. Okay, so a priori could be infinite. But we prove it's not, like here, right? And then, so this is the first application. So application number 2. So this is related to what is called conformal measures in dimension 1, or like Parsons-Sullivan measures for rational maps. Okay, so let me state the theorem. Okay. So now we add assumption. So F is hyperbolic. What does this mean? It means F is uniformly expanding near the Julia set. So uniformly expanding in the same sense, like as the smooth ergodic theory, uniformly hyperbolic. Hyperbolic holomorphic endomorphisms of D greater than or equal to 2. Then we have the following. So delta J of F, which I'm not going to define. So this is going to be the conformal dimension of the dynamical system. So basically, it's the smallest exponent where there exists a, we call volume conformal measure. Okay, so this is equal to also the same, 0 of the pressure. And now it's equal to 2 times the volume dimension of the Joule set. So basically, for sets and measures, we're going to define what is the volume dimension. And this is also, like, if you look at the statement, right? So this is also in the spirit of Bowen. I should add here, so where Bowen proved that, well, actually his theorem works in more generality, that the first 0 of the pressure is the House dimension of the limit set, right? So, well, like we have 2 here for the same reason. Yes, yes. So, yes, like Bowen-Rural kind of formula. Right. Okay, so what is this? So now we want to define what is the volume conformal measure. So in dimension 1, it is the conformal measure that is defined by Urbanski-McMullen, like independently. Okay, so definition. So given t greater than or equal to 0, what is the t volume conformal measure? So a probability measure nu is t volume conformal. Well, it's slightly misleading because in higher dimensions it's not conformal, but we want to just match the name of conformal measures in dimension 1. So it's t volume conformal if for any Borel subset A of the Joule set on which F is injective. So we have the similar kind of formula as in dimension 1. So then we'll have the measure of F of A, the image of the set under F is equal to the interval you integrate on the set A of Jacobian, which is F prime in dimension 1, complex Jacobian, to the power of t, which is t volume conformal of the measure d nu. Okay, so any measure satisfies this equation is called t volume conformal. And in dimension 1, this is the conformal measure, as in the sense of McMullen, Urbanski, Denker-Urbanski. Okay, so yeah, so what is this delta J sub F? So this is the conformal dimension of the system, which is the inf of t greater than or equal to 0, such that there exists a t volume conformal measure on the Joule set. Okay, so basically this is the statement of the theorem. So it's like up to here. Okay, so I'm not going to prove these two theorems because it's kind of like a different proof from the proof of the first theorem. So I have roughly 10 minutes, so 11 minutes, very good. I'm gonna tell you kind of the rough idea of how to prove the main theorem, like what is this volume dimension? So proof okay, so like if we want to prove some dimension equals some number, right? So what is the strategy? Well, you have seen the strategy both in the last BIANCHI conference and this BIANCHI conference. You first prove this measure is exact dimensional, right? But here, we want to, so before, I think, maybe let me just write here. What do people mean by exact dimensional? So you first define a local dimension, right? And then which is basically you take a measure and you take a ball. So it's local at the point X. You take a ball of radius R, and then because your system is a compact metric space, so in our case, we work on CPK. There's Fubini-Studio metric. So you can take a ball of radius R, and you take what is the measure of the ball, right? And you take a log of this number and divide it by log of the radius, right? And then basically you prove for nu almost every x, this local dimension, this is the limit. This limit exists and it equals the constant. And the constant is the constant you want. Okay, so in our case, we want to define a different local dimension. And basically you prove for nu almost every x, this local dimension, this limit exists, and it equals a constant, which is entropy over Lyapunov. Okay, so let me just write down what is this local dimension. But it's not going to be very precise, because within the definition, there will be sets that I have never defined. Okay, so so we define a local dimension, and we will have many parameters, epsilon, kappa, n. And I haven't said what is this. Okay, so this is defined as log of volume of a set, which I'm going to call U x epsilon kappa n. Yeah, so basically, like tomorrow, I will just say what are these sets and why, if we define things like this, then we can prove the theorem. Okay, so oops, sorry, I should write here. The new measure of this set. Okay, and downstairs is the volume, the Fubini-Studio volume of these sets. Okay, and then the exact volume dimension says that, so basically like, let me just write as a proposition. So for every nu inside this set, so F invariant ergodic probability measures with positive Lyapunov exponents is exact volume dimensional. What does this mean? It means for nu almost every x, we have the following. So we have, okay, so lim inf as epsilon goes to 0, lim inf as kappa goes to 0, and lim inf as n goes to infinity. Of this delta x epsilon kappa n, it equals the lim sups. And this is a number. And this number is the number you want. So this is the entropy over sum of the Lyapunov exponent. Okay, so this is the first step of the proof. So you prove this limit exists and it equals the entropy of entropy over twice some of the Lyapunov exponents. Almost. Yes. Yes. Yeah, exactly. And then after this, right? Well, I guess like for this audience, like I think Francois also mentioned that 2 years ago, there's an argument in Young's paper. So basically, Lysong in her 2082 paper. So basically, there's the proposition or like a method which tells us how to go from local dimensions to house dimension, or in here for volume dimension. So basically, like you want to prove the volume dimension of the measure is bounded above, where I omitted a lot of quantifiers, bounded above by this number, all the limb sups, and also bounded below by all the limb nymphs, right? And if you prove this is constant, then you know the dimension of the measure is this constant. So the second part, step 2, is you take Young's paper and figure out how to make it work for volume dimensions. So basically, yeah, so basically you want to prove, okay, maybe volume dimension of nu is bounded above by the limb sups and bounded below by the limb nymphs of this local dimension. And then because this is a constant, so this is how you prove this equals entropy over twice the Lyapunov exponent. Okay, so I think I will stop here, and I will continue tomorrow with more details.
Any more comments?
Oh, yes. So let's say, okay. So let's
Roughly. Should we just sort of take that almost as a definition? Is that the best way to?
No. This is the local dimension. So
Right.
the volume dimension means you take a set, and first, what is this epsilon? So basically, like for technical details, we need to put some.
We can skip technical
Yeah, so,
if you want.
so basically, like, we need to take sets at the level of epsilon. We do all the, it's kind of like you take a set y, you look at y epsilon at the scale epsilon, and you cover by, not balls, but by these U sets. And just like the house dimension, so you take the sum of all the elements in the set, but instead of diameter, you take the volume to the power of alpha. And then take the inf, and then take this limit and prove something like a house dimension. So as alpha goes to infinity, so first so there's a cut. So this sum is going to be infinity for a while, and then it jumps to 0. And then that jump cut will give you alpha, and then you take epsilon goes to 0. And then prove that will go down. So that's kind of like a house dimension.
And the sets U are dynamically defined?
Yes.
So they are
basically
like,
they are pre-images of balls. Yes.
so they're like Bowen balls of a certain.
Yeah, exactly. And
So do K and N relate to the, kappa and N relate to the size of the Bowen balls?
Yeah, and N is the iterate.
N is the number of iterates and kappa is the diameter or something like that?
Like radius of the balls you want to.
Got it.
Yeah.
Okay.
Yeah.
That's great. Thanks.
More questions or comments? Please, Daniel, 1 second.
So you said when the Lyapunov exponents are the same, the volume dimension coincides with twice the house dimension.
Yes. So basically these sets are roughly balls.
So are there other situations where you can explicitly relate it, give the volume dimension coincides somehow with something that does not depend on the dynamics, can be expressed in terms of the house dimension?
Only when the Lyapunov exponents are equal, right? Like,
As if only if?
yes, yes. And then, like, yeah, in general, this volume dimension is smaller. I mean, twice the volume dimension is smaller because you're covering sets with more efficient, like these are dynamical quantities, right? These are sets coming from the dynamics. So you're covering your sets more efficiently according to the dynamics. So, yeah.
Thank you.
More questions, more comments? Well, if not, let's once again the speaker.